Everyone. Today we are going to talk about electric charge and electric field. So the first thing we need to talk about is static electricity, and this really started the conversation of what is going on here. So we have a couple of funny pictures, in my opinion. We've got a cat with a bunch of packing peanuts stuck on it, and then a balloon with some paper stuck to it. And so this is static electricity, where we have some sort of charges or something going on between these two objects to allow them to kind of stick together. And this is what interested scientists and people in general to start looking into this. So here are some specific observations of electric force. So this is a force that acts without physical contact between two objects, meaning these objects don't have to be in physical contact with each other in order to act upon each other. This force can be repulsive or attractive, depending on the signs of the charges, and we'll get into that a little bit later. But if we have two opposite signs of charge, then we will have an electrostatic attraction between the two objects. And if we had similar signs or same signs, we will have an electrostatic repulsion. So they would not be attracted to each other, they would repulse each other, or repulsive. Okay, not all objects are affected by this force. So certain materials are, but not all materials. And the magnitude of these forces decrease rapidly with increasing separation distance between the objects. So much like gravity, it has an 1 over r squared relationship with its magnitude of the force. So we have a couple of examples down here. We have just a cloth and a rod that has positive charges. The cloth has negative charges, and as you can see, they are coming closer to each other. They are attracted to each other. On the other hand, if we have a positive charged rod coming next to a positive charged rod, they will re repel. And then same thing with the cloths. If we have two that are negatively charged, bring them close, they will repel as well. Okay, so now we need to talk about some properties of electric charge. Now, charge is something that can be quantized. We can have a value to it. Electric charge comes in discrete amounts, and that amount is 1.602 times 10 to the negative 19th coulombs. Okay, that C means coulomb, and that is the SI unit for charge. And this value can either be positive or negative depending on the charge type, if it's a positive charge or a negative charge, and all that changes is this sign. So positive charge, you'll have a positive value, negative charge, you'll have a negative value. Makes sense. We should also note that charge is conserved. It cannot be created or destroyed. And charge is also conserved in closed systems. So we have a law of conservation of charge, and this tells us that the net electric charge of a closed system is constant. Now let's talk about the charge that's carried by electrons and protons. So we have a simple model of an atom. We have negative electrons that orbit a overall positive nucleus that has positive protons and neutral electrons in it. So this was the base idea of an atom. Of course, now it's evolved a little bit more where we have an electron cloud rather than little, orbits, very specific orbits that it stays in. Like we used to call them shells, but now they are electron clouds surrounding a nucleus. And the magnitude of a basic charge, Q, is going to equal 1.602 times 10 to the negative 19th coulombs, like we just talked about. We should also mention that the number of protons to make 1 coulomb is going to be a simple conversion, and we obtain 6.25 times 10 to the 18th protons. And we also have an image down here of a carbon atom. So we have protons and neutrons in the center, in the nucleus, and then an electron cloud surrounding it. Okay. So let's talk a tiny bit more about the law of conservation of charge. So again, total charge is constant in any of these processes. So we can separate charges in atoms, but the existing charges are moved around. They're not they're not created or destroyed. So they're just kind of moved around, maybe swapped a little bit. So we have, say, amber and a cloth, and we have net charges of these um, uh, objects, sorry, I couldn't think of the word, objects of 0, these net charges are 0, we bring them together close into contact to where we have some sort of exchange of charges, we can then get overall net charges that are different than before. So this amber is now a net charge of -2, and the cloth is a net charge of +2. So this is, again, the law of conservation of charge. Overall, in this system, we still have a net of 0. Okay, now we can talk about conductors and insulators. So some electrons in metals and similar conductors are not bound to individual atoms or sites in the material, and these are called free electrons. So they can move through material, sort of like maybe air goes through loose sand or something like that. It can just move around. Now, a conductor is going to be any substance that has free electrons and allows charge to move relatively freely through it. So, good conductors are metals, salty water, molten salt, wires, as we'll see. And then we have the complete opposite, which is going to be an insulator. So these are substances that don't allow any charges to move through them, such as glass, pure water, dry table salt, rubber, plastic. So a really good example of this would be like our chargers, phone chargers. This is a computer charger. So inside we have wires, and so that's our conductor. It moves electrons through it completely freely. They're able to move through it. And then surrounding those wires, we have insulators so that we don't have any sort of flowing out of these wires. So it just goes along the wire, and then, using it to charge your phone or your laptop, whatever it may be. So this is very much in a day-to-day, day-to-day usage. All right, so we can start to talk about charging by induction. And so this is going to be charge that's created with a nearby object, but does not come in direct contact with it. So, for example, if we have a neutral conducting sphere with charge distribution, we have pluses and minuses all along it, and then we bring over a positively charged rod. Okay, so in the beginning, which they didn't, I don't have a picture of like before we introduced this charged glass rod, but this would initially just have a very standard distribution, pluses and minuses all throughout the surface. Now, when we bring this positively charged glass rod, the negative charges will align since they have an attractive force between the two. Between the positive and the negative charges, we have this attraction. So these negative charges will kind of line up on the side here, and we will have this induction that happens. Okay, so we are inducing a charge. Now, We can also have induced polarization of neutral objects. So polarization is the separation of charges in an object that still remains neutral, which this would actually be one exactly. And this results in a formation of an electric dipole. Dipole meaning two poles. Makes sense, right? So we talked about this one. We can now talk about this one. It's very similar. We have positive charges coming into contact with something that's neutral. The negative charges are attracted to it, but it is still overall a neutral object. It's just kind of realigning it within its substance. Same thing with B here. We have positive charges on one end and negative on the other because we have introduced a negatively charged rod, glass rod into the situation. Okay, and this is something that's really cool phenomenon that happens if we have a charged rod and we have water that's flowing next to it in a stream. We can bring that close to the stream of water, and it will start to bend, it'll start to curve since it has the attractive forces between them. So here is another example. So say that we have two, I don't know what these would be called, but we have two of these objects that are neutral. We bring a charged rod into contact, or close contact. I wouldn't say they actually touch, right? But close enough. And this causes a separation of the charges. So now we have this positive rod that came close to this left-hand side ball here. And now this side of the ball has negative charges. And so the other charges will switch to this other one on the right-hand side, and it'll be all positives, okay? Now, once we separate the spheres, okay, we still have the glass rod here, so say we just move this right one a little bit away, so we separate these spheres, and then remove this charged rod from the situation. Now we have both of these spheres are now charged. One has a negative charge that was closer to the glass rod, and we have a positive charged one that was further away. So this is another case of induction. All right, there is one more way we can induct or charging by induction using a ground connection. So first we have these two charges, and we're just coming into close contact, again, not touching, but close contact, so that we begin to have a dipole. We will then connect the sphere to a ground, and we'll talk a bit more about that later on, but we ground the sphere, and we will then have some negative charges being attracted from the ground to this sphere, okay? And after some time, the ground is removed, and we still are left with these negative charges on the sphere. And so now our sphere has an induced charge, and it is a negative charge. Okay, so I'm going to pause here, and then we will pick up again at Coulomb's law.